What's up, you guys? This is Stateful here. I know it's been a while, but we are finally back with an interesting video. So today we're going to talk about the cloud and the cloud native topologies. This is going to be a long workshop where we will be discovering many terms and tools as shown in this diagram here, and we'll end up having a fully cloud native ecosystem that's ready to be running on the cloud. Now, before we delve into this, I'm just going to point out some recommendations. And I'm not going to use the word requirements here because even if you don't have a background in the cloud or in cloud native technologies, it's completely fine. You can just sit back and relax as I'll explain all of the stuff that I'm going to talk about here. If you have worked with Java and Spring before and have got some basic scripting and configuration knowledge with Linux, this is going to be very easy for you. But again, we're gonna go through all of the stuff, explaining every bit, so we're gonna be fine. Now, without further ado, let's start our session. So before understanding what cloud native apps are, let's remind ourselves of what cloud is. All right, so what does cloud mean by definition? So the cloud is an IT infrastructure that guarantees the delivery of computing resources to consumers following a model which is famously known as the cloud computing model. Now, we're going to explore this model in details in just a bit, but before that, let's understand how this cloud works. So just like water, electricity, or internet, the provider, which is in our context, the cloud provider, manages the underlying infrastructure. So consumers don't have to worry about all the physical resources like VMs, storage, network, etc. This is really great. Now, there are three ways this cloud infrastructure can be deployed. We call them deployment models. The first one is going to be the private cloud. Now, with this type of deployment, the organization manages all the resources. So this is usually the case of banks, for example, or government systems, or any system where data is really sensitive. This can also be related to some compliance with specific laws or regulations like the General Data Protection Regulation. We also have the public cloud. Now, with this model, the infrastructure is provisioned for public use. It's usually owned by an org, the cloud provider, so the physical resources are on the provider's premises. Examples of this model, we have AWS by Amazon, we have Azure by Microsoft, we have Google Cloud, Heroku, Oracle Cloud, and the list goes on. And the last one, which is going to be the combination of the other two. So in the case of hybrid cloud, computing resources are used from different environments. Now, we previously mentioned the word cloud computing model. Actually, we have 5. So to better understand this concept, we'll follow some kind of pattern here. So in our system, we have different layers, and the more we go up, the more there are abstractions. So in each model, we will determine what is provided to the consumer to manage and what is abstracted from the consumer. Now, in infrastructure as a service, the platform gives computing, network, storage, and also takes care of the virtualization. So the consumer has to provision, manage, and configure the servers aka virtual machines, using middlewares. Now, example of services for this model, we have EC2 or Elastic Compute Cloud in AWS or Azure virtual machines. So in container as a service, the consumer cannot control the virtualization of the resources. So all they have to do is provision the container, and the provider does all the background stuff, which is usually done using tools like Docker Swarm or Kubernetes, which is the most used nowadays. So examples of this model, we have Elastic Kubernetes service by AWS or Google Kubernetes engine. In platform as a service, we have even more abstraction. So the developer can simply deploy an artifact, a jar, for example, and it will be provisioned automatically with a Java virtual machine and even with some extra middlewares and services like a database, for example. So in this case, we can talk about the Elastic Beanstalk, which is provided by AWS. In function as a service, we rely on the serverless computing, meaning we don't actually have to worry about the server or the infrastructure. We only have to take care of the business logic, which is a bit of code that is going to be triggered by an event. So examples of this model are Lambda or Azure functions. And finally, we have the software as a service where everything is abstracted. So the consumer only has access to the application while the provider manages all of the stack of the software. You probably have encountered some examples of this, like Microsoft Office 365 or GitHub, for example, etc. Now, the main characteristic of the cloud is the term elasticity, meaning cloud resources are provisioned on demand and then they are released dynamically. So you don't have to actually predict the maximum or minimum usage of resources. So no more resource usage prediction. And that means you only have to pay for what you actually use. So pay on demand, which is really beneficial. So far, we have a general understanding of the cloud and its main benefit. Now, how do we make our apps benefit from this? So how can apps benefit from cloud? And that's where the term cloud native comes in. So these so-called cloud native apps are designed to adapt to the characteristics of the cloud. So let's see what makes an app cloud native. So the first thing that comes to our head when designing cloud native applications is the term scalability, meaning the application can support increasing workloads if provided with additional resources. Now, we have two types of scalability. Vertical scalability, which is achieved by adding hardware resources or removing them. So we can either add CPU or RAM, for example, so plus, minus. And this is the old way of doing things. In fact, there are still legacy apps which use this type of scaling. Obviously, this is not really good in the cloud, as you can't scale infinitely and you would be allocating huge resources that most of the time are not being used. On the other hand, we have horizontal scalability, which is achieved by adding instances, nodes, containers, or removing them. Now, this is very important in a cloud environment as the resources are dynamic and constantly changing. Remember the word elasticity here. So we can spin up instances or shut them down quickly to obtain our needs. But this requires the app design to be ready for this kind of scalability. So I'm just going to put a requirement here to say that our apps need to be scalable. Now, there are a lot of things to consider when designing scalable applications, and the most important one, in my opinion, is state. See, you can't really have two instances running simultaneously, each having a different state. That would create inconsistencies. So to avoid that, it's better to make your application stateless and move that state to a more dedicated component, aka a stateful component, which can be a database, for example. So what do you need to remember from all this? Basically, cloud native apps must be horizontally scalable. We also have other characteristics that are important in cloud native topologies. We can mention observability, which serves as a purpose to deliver output to our distributed system. These outputs can be logs, metrics, traces, etc. The observability can be achieved by monitoring specific aspects of the application, like health, status, for example, using Spring Actuator, alerts and dashboards that show us the data in graphs. For example, we can use Grafana in this case. We also have traces to see the flow of data through distributed systems. We have open telemetry and Grafana tempo that can help us do that. And last but not least, we have log and log aggregation to debug failures. Here we have Loki or Fluent Bit, etc. We'll be using a lot of these tools later on in the workshop. Next up, we have resilience, which is the ability for the app to provide service even in a faulty state. It is always important to make your app available because in the cloud, resources and configurations are constantly changing. So we have to design our app to adapt to that. So let's say we always have a response to avoid cascading failures. Now, when we talk about resilience, we have three concepts. And the first one is faults, which can be caused by null values being returned. Now, this fault can bring us to the second concept, which is errors. Now, an error can be, for example, a null pointer exception. This null pointer exception, if not treated or not caught, can cause system failures. In this case, a 500 error can be returned from the server. So an essential job for the developer is to make the system resilient and fault tolerant, meaning that faults should not be allowed to cascade to other components of the system. Now, there are countless ways to help ensure this. We can implement, for example, circuit breakers. There are also rate limiters. We can do timeouts also, etc. Again, we're going to explore these solutions in details later on. Next up, we have loose coupling. What does that mean? Well, it is essential to make our system modularized, composed of modules. Each are as independent as possible. That way, when one of them is changed, the others stay intact. Now, you can achieve this even in your monolithic design, which is the opposite of modular / microservice design. We can do this by implementing contracts with interfaces. So we make APIs for each module, ensure that the don't repeat yourself pattern is used. So never copy paste code from other features in your app. We also have separation of concerns. The main point is that it's not always necessary to move to microservice architecture to achieve this capability. The last thing I want to point out is manageability, which is the power to make your application as configurable as possible in order to make it easy to modify its behavior without the need to change the code inside. We have many examples of this with Spring Cloud config, for example, and even with Kubernetes config maps that we'll explore later on this section. You might have heard about applications being deployed on different environments using the same artifact. Configurations such as data source and certificates will be applied differently depending on the environment. So for example, we have one for dev and one for production. So we'll explore how this can be done later on. All right, so it's also important to talk about the best practices when using cloud native topologies. So let's do that. So in cloud, it's highly recommended to make your system automated, building the app, deploying it, even provisioning the infrastructure to manage the configurations. Again, the importance of manageability here. So let's say automated resource provisioning. So this can be achieved by what we call infrastructure as code or configuration as code. So for example, instances are deployed, increased and decreased automatically through auto-scaling groups, more on them later. And you can automate these systems with tools like, for example, Terraform, which provisions servers, networks, storage, etc. You simply put a code in a version control system, and you have all your resources provisioned in the cloud automatically. This way we avoid manual configuration, so no more manual configuration. We also avoid instability of servers, and every change in the infrastructure is tracked, so traceability by source control. So risks are reduced. There's actually a common term used when something is this independent of change. It's actually called immutability. So basically our servers in the cloud would be immutable, so they are not changed after they are deployed. If any change is necessary, it's only done through configuration code. In every change, old servers will be down and new servers will be deployed with the new changes in the configuration. Next up, we need to respect the continuous delivery contract, which indicates that our software needs to be deployed continuously and reliably at any time possible. So we can make frequent and impactful changes on short periods. For example, each week we deploy a new artifact without causing any troubles such as regressions, faults, etc. This is achieved by continuous integration. So at each commit, the software is automatically compiled, then it's tested and packaged as executable artifacts, such as jar files or container images. If any issue is detected, it should be fixed immediately to keep everything stable. After that, we have the continuous delivery phase. So after an artifact is properly produced, it goes through additional tests, such as user acceptance tests, security tests, compliance, any test that might increase our confidence in that artifact. So this continuous delivery allows us to always trust this automated way of delivering our product. All right, so let's discuss the different cloud topologies that are commonly used nowadays. So we have containers that are components sharing the same kernel as the host. This came after the virtualization. So traditionally, you would need to install the Java runtime environment to make your application run in the virtual machine. Now, the container comes shipped with everything you need in an image, which is a blueprint. And it's completely independent of the application, so these lightweight components can be shut down and deployed very quickly. Now that we have containers in our pocket to make things more organized, as you would probably have a lot of containers running and a lot of startups and shutdowns, it can be a mess sometimes. That's why you need to have an orchestrator. So we move from manually constructed nodes to a cluster of nodes, which in a container as a service context, a tool like Kubernetes is going to grant us all the orchestration of these containers. So scheduling new ones, exposing them to the outside, opening ports, configuring a resource allocation, many things that can be discovered later on. The point is that you only need to configure your resources once using YAML files, and Kubernetes will then provision everything for you, which is very powerful. Serverless technology can play a huge role in your system in many particular cases. When you don't want to worry about provisioning a server, just go serverless. You could do so by making functions that execute business code, nothing else, which can be triggered by some events. You can use serverless as well by relying on third-party services, which there is another term for that, which is called backend as a service. So, for example, a database or an authentication service that can be deployed as serverless architecture. These services, either functions or backend services, are only up when they need to make a response to the client. If there's nothing to process, they're completely down. And here you could automatically see the money that you've saved compared to when using the normal orchestrated containers or VMs or servers, etc. You get the point. For the record, you can architect your application to be a monolith, meaning the app is one unit divided into three parts: data layer, business logic, and presentation. But I would recommend to use microservice. There are many reasons for this. I could go forever, and this would defeat the purpose of the video as it would make it much longer. But when you're working with microservices, you have many components that work independently, each its own database, trying to accomplish one functionality in your system. And this helps us a lot in the cloud. I'm not saying that monolithic apps are wrong, it just depends on your use case. But since cloud native apps are distributed systems, just like microservices are, we are going to choose the microservice architecture for our system. Alright, so our app's design is going to have three categories. So the first one is going to be application services. So these are stateless microservices that are implementing a certain logic or feature. The second one is data services. Now these are stateful, and their whole purpose is to store data. These can be databases such as PostgreSQL. For the cloud, if you have worked with AWS or Azure before, you might know DynamoDB or Cosmos DB, etc. Between these components, we have the third category, which is the integration component, essential to assure communication between the other components, either synchronously with a request-response approach, or asynchronously using event-driven approach with tools like RabbitMQ, for example. There are a lot of other topics that we can discuss, like concurrency, for example, in stateless scalable apps. So if you have many users using your app, you need to think about how you're going to distribute the workload and process in your system to avoid inconsistencies and unavailabilities. Another aspect that we can talk about, obviously, security, which is a cross-cutting concern. So a cross-cutting concern is mainly code that exists in your app, but it's separate from your business logic. It's a design pattern that's applied throughout the lifecycle of your app, like logs, transactions, etc. Anyway, to get back to the security part, obviously we don't need to talk about how security is crucial for your system. Just to keep things brief, maybe dive into details when we implement it later. But when we talk about security in cloud native apps, we talk about authentication and authorization. So authentication is proving that the user is who he claims to be by providing his way of identification, and the authorization, which is determining if that user is allowed to perform that specific action. So for the most part, we will implement the OAuth 2 standard for our apps, but we will explore it more later in the workshop. I think this should give us a basic understanding about what we're going to discover in our workshop. I know it's a bit of a lengthy introduction. I hope I haven't forgotten anything that we might need later on. If so, no worries. We're going to go in depth throughout the whole thing. Okay, so you might have guessed from the tools that I've mentioned that I'm going to use Spring as the technology, simply because it's a pretty rich ecosystem nowadays. And there are a lot of Spring projects like Spring Data, for example. There's also Spring Integration, Spring Config, etc. So the best option for cloud apps in a Java ecosystem, in my opinion, is Spring Boot. It's standalone, ready for production, and has a lot of default configurations. So unlike the traditional Spring project, where you would configure all of the things by yourself using beans and XML files, Spring Boot takes an opinionated approach, meaning that it takes all of the default best practice configurations and bundles them as starters in jars that you can use directly in your project. So it's super powerful, and we'll see that in a bit. It also has an embedded Tomcat server, so instead of the traditional way to package the app in was or is that later need to be deployed on application servers, so maintenance of these components is mandatory. Here in native apps, we aim for self-contained components. So we have a jar that's simply going to be executed by the Java virtual machine. By the way, Spring is pre-configured with Tomcat, but you can change it to Jetty if you want. So for our project, we're going to design a management system of some sort. We'll keep it simple. Let's say an online restaurant application, for example. Now, we'll start with the first microservice to make it as simple as possible. So we'll make a single use case. So a user can manage food menu in the app by adding, deleting, consulting, etc. Which basically means the app showcases and manages different food that this restaurant can provide with their prices, etc. You get the point. No other use cases like ordering, since we'll delegate other processes to future microservices. So the actor in this case is the user. It could be visitor, admin, whatever, and the system is going to be the restaurant.